كده قابلني. Okay.
Hi, so welcome everyone to the next seminar. So today we're going to have Professor Peter Bartlett. He's the Associate Director of the Science Institute for Theory of Computing and also a Professor in Electrical Engineering and Computer Science. It's also Statistics in UC Berkeley. And he has done a lot of work in machine learning and also statistical learning theory. And so I'm going to have to risk his really long bio. But he has written a book on neural network learning. He has been the Institute of Mathematical Statistics Medallion lecturer, winner of the Malcolm McIntosh Prize of the Physical Scientist of the Year, Australian Laureate Fellow, Fellow of the IMS, Fellow of the ACM, and also Fellow of the Australian Academy of Science. So today is actually it's our great pleasure to have here visiting us, and he's going to talk about a very interesting topic on benign overfitting.
Thanks, Owen. All right, thanks very much, Owen. Thanks for inviting me here. I'm delighted to be in Vietnam for the first time. So this talk is some joint work with Phil Long at Google, Gabo Lugosi at Pompeu Fabra, and Alex Sigler, who's a PhD student in statistics at Berkeley. And it's this phenomenon of benign overfitting that's been observed in deep networks. So one of the really surprising and mysterious things that we've seen about deep learning is that deep networks can be trained to essentially zero error on the training set, even for regression loss. So we're really nailing those predictions on the training data. And still, the predictive accuracy on subsequent data, on independent test data, is really quite good. Maybe not the best you can get, maybe not state of the art, but close to state of the art. And that's especially surprising in that it's true even when there's noise in the problem. So this is a case where there's indisputably significant noise in the problem because it was added. This was an experimental result due to these folks who were at Google at the time, looking at the performance of very standard deep learning methods on a pattern classification data set, so CIFAR-10. And on the x-axis in both of these plots is the proportion of the examples for which the label information was corrupted. So as you move across from 0 to 1, you're going from the correct labels to 100% of the labels are just randomly assigned in the training data. The point of the paper was that you can actually get to zero training error even when the labels are completely random. So there's no information about the relationship between these x's and y's on the right-hand side here, but you can still perfectly fit every training example. And the plot is showing the time until you get a perfect fit, and the second plot is showing the performance, so the predictive accuracy on an independent test set for the same thing with no corruption. This is the proportion of examples that are misclassified for one particular architecture and inception architecture. And as you increase this proportion, you see you get this, rather graceful degradation of the predictive accuracy until you reach this point where, of course, there's no information. You just predict as well as chance. 10 classes, you get a 1 in 10 chance of getting it right. So the really striking thing is that for every point along this curve, you're getting a perfect fit to the training data, even though the training data is noisy, and yet accurately predicting. So that's a really striking thing, and something that has been observed in a bunch of other contexts. So Belkin, Sumar, and Mandal did a rather extensive experimental study looking not just at neural nets, but all sorts of other prediction methods, and saw a very similar phenomenon. And it really goes against a lot of the conventional statistical wisdom. There's no trade-off possible here between the fit to the training data and the complexity of the prediction rule that you end up with, which is kind of the classical thing that you would expect in these prediction problems. But if you're getting a perfect fit to the training data, you have nothing to give up in terms of choosing the right complexity of the prediction rule. And as I'll point out, that's especially surprising given that we're getting a perfect fit. So a perfect fit is certainly overfitting. You can't hope to fit any better, but that overfitting is not hurting. So it's a phenomenon of benign overfitting. We're used to hearing overfitting, used in a pejorative way. Right? So if you fit perfectly, that's a bad thing. You're overfitting. So here we're getting a perfect fit, but still predictive accuracy is not so bad. And the statistical wisdom, of course, says there should be this trade-off between the fit to the training data and the complexity of a prediction rule. So if we think about a regression problem, for instance, where the fit to the training data might be measured by the sample average of the squared error on the training examples, these xi, yi pairs, for our prediction rule f hat. And we might measure the complexity of the prediction rule in terms of the number of parameters that go into this function, or perhaps the norm of some kind of norm of the parameter vector, perhaps some kind of equivalently or more generally, I guess, the norm of this function if it lies in a reproducing kernel Hilbert space. We might think of that as a measure of complexity, or in some of these other the classical non-parametric methods, the bandwidth of a smoothing kernel that we use to define this f hat. So all of these different kinds of notions of complexity, we're used to trading off how well we fit the data with the complexity of that prediction rule. And as you fit the data better, you expect to get a more complex prediction rule and pay for that in terms of the statistical cost. As you restrict the complexity, you expect to pay for that in terms of the fit to the training data, and so you get an additional approximation error. So that's the classical perspective. And taking this sort of perspective, particularly being careful about controlling the complexity of the prediction rule is especially important if you're working with a non-parametric method, right? A method where the number of parameters is growing with the sample size. And there are lots of examples from textbooks that say this approach of interpolation is just a silly thing to do. Right? So Sasha Rachlin pulled out a bunch of these. This was from a boot camp lecture series that he and I gave in May this year. But this is the Hasty, Tibshirani, Friedman text on statistical learning that says, with too much fitting, this is the classical picture. As you increase model complexity, you get a better and better fit to the training sample, but performance on the test sample will get better and then worse as you necessarily are increasing the complexity of your prediction rule. With too much fitting, the model adapts itself too closely and won't generalize well. Interpolating fits are unlikely to predict future data well at all. This is from Giaficola, Kujak, and Wok. That say, if you interpolate the data, this will lead to a function which interpolates the data and hence is not a reasonable estimate. These are the examples that we use in machine learning classes, right? You don't want to be doing the thing on the left because you're fitting too well, you're getting something that's too complex, you don't expect it to predict well on subsequent examples. And yet this is, seems to be what's going on with deep learning methods. So that's a really, statistical wisdom tells us that we shouldn't be interpolating the data, that a prediction rule shouldn't fit too well, there should be this trade-off, but that seems to contradict what's observed in practice for deep networks. So this is really a new statistical phenomenon that has been revealed by deep learning methodology. Okay, so I think attention focused on this phenomenon at first at a Simons Institute program on foundations of machine learning in the spring of 2017. There were a group of us there that had a bunch of discussions about this. It came up out of some bootcamp talks in that Simons Institute program. Misha Belkin and Daniel Su were two of those, and they worked out, I think the first outcome of those discussions was this work on simplicial interpolation, which is related to a nearest neighbor kind of a method. If you think of one nearest neighbor as doing something like, it's certainly interpolating, right? But we know that one nearest neighbor doesn't approach the Bayes risk. You pay a cost for interpolating with a method like that. This is similar to nearest neighbor in the sense that you're not, the neighbors are defined by doing a triangulation or forming a simplicial complex with the data and then looking at a prediction that linearly interpolates for every point. You find that simplex and the corners of the simplex, you take those labels and then linearly interpolate those. Right? So this is a method that certainly interpolates at all of the data points. And actually this paper showed that, skipping ahead, this paper showed that as the dimension gets large, the excess risk of this method goes to zero. So you do get good performance out of this particular interpolating method. Same paper had another more classical kind of non-parametric approach, kernel smoothing approach, Nutter-I-Watson estimator, and considered that kind of approach with a kernel that was a little bizarre. So this smoothing kernel approach is to, the bottom line is just normalizing. So what we're doing here is saying, if we see an x, we should predict according to how close x is to one of the examples xi in the training set, and use that yi. So we're going to mix all of the yi's from the training set according to how close we are to the corresponding xi. So this k sub h is a kernel that measures the similarity of x and xy, if you like. But the funny thing is here, these kernels are singular. That is, they go to infinity at 0. Right? The h is a bandwidth parameter that's just adjusting kind of the roughness of the function you end up with. But these things are singular. They have a 1 over norm of distance from xi to some power. Okay, so at the data point, the weighting goes to infinity. So then when you normalize, you get something that interpolates. Think of the continuous approximation of that, the limit of this value. So for these kernels, you could show actually that you can even achieve, if you choose the bandwidth appropriately, you can even achieve minimax rates, and you're certainly interpolating, right, because of that singular property. And there was some related work that Misha Belkin did with Sasha Rakla and Sasha Sibakov with slightly different kernels. There's also been work on linear regression in this setting. Kernels specific kernels, so I guess infinite dimensional linear regression with those kernels defined in terms of Euclidean inner product. And I guess in both of these cases, they're considering the dimension of the input growing as the sample size grows. And then looking at what happens when you have an interpolating solution in that case. Yeah, mainly using the tools, I guess, except for this very recent work, maybe using the tools of random matrix theory. So under the sort of assumptions that come up there, understanding the asymptotics as the dimension of the input and the sample size go to infinity together. Okay, so this is the most closely related to the results I want to tell you about today. But our results are for any dimension, any sample size. We get quantitative results, actually upper and lower bounds that are separated by a constant factor on this case of linear regression. So we're focusing here on the kind of simplest prediction problem where we might observe this bizarre phenomenon of benign overfitting. And that simplest example is linear regression. I'm not advocating this as an approach to coming up with a linear prediction rule, more trying to understand this phenomenon that's seen in deep learning and seeing, in a simple situation where we have tools to analyze what's going on, what's behind the phenomenon. So it's more aiming at understanding this phenomenon in deep learning by looking at a simpler setting. Okay, so let me talk about that simpler setting of linear regression. First of all, we'll get on to saying, what are the connections to deep learning? What are the implications for some other phenomena that have been observed in deep learning a little later, but let me start with this linear regression setting. So the problem here is just prediction. We've got an input space that's that you can think of as just being Euclidean space, but we can also cope with a Hilbert space, so in the infinite dimensional case. Our predictions are linear functions of the inputs. So we have our covariates, think of that as being a vector in RD, or maybe D is infinity. We have a real valued response, and we get training data in the form of these XY pairs, and we'd like to choose a good linear function from X's to Y's. Okay, so in stating the results, I'm going to make the assumption that these XY pairs are mean zero jointly Gaussian. That's not essential, and I'll be a bit more specific about how we can generalize that later, but the brief summary is we can deal with sub-Gaussian XYs as long as we're in the well-specified situation. So the conditional expectation of Y given X is a linear function. But then the assumptions are just these sort of classical tail assumptions where we've got something like Gaussian tails. But let's think about X and Y being jointly Gaussian and mean zero. Then there are three parameters that tell us essentially all we need to know about the linear regression problem for the purposes of this talk. There's the covariance matrix for the X's. So X's mean zero. This is just the second moments. We can write them in this uncentered way because the expectation of X is zero. And I'm going to write that covariance matrix as write the spectral decomposition of that covariance matrix, and in particular the crucial quantity here are these eigenvalues, the lambda i's. All right, so and we'll see, at the heart of this benign overfitting phenomenon in linear regression, everything depends on what those lambda i's look like. Okay, so this is important notation to remember for the rest of the talk. Another of these important parameters is the optimal, the parameter vector of the optimal linear prediction rule. We think of that as the theta that minimizes the expected squared error of the linear prediction, X transpose theta. So that's what we call theta star. And then sigma squared, little sigma squared, is the corresponding expected squared error. So in this linear regression setting, we're using linear functions to map from X to predictions of Y. We're measuring our performance by looking at the expected squared error of our linear prediction, okay, of that outcome. And this is the best possible performance, right? The best, the smallest expected squared error for any of these linear prediction rules. And you'll see I'm using, vector and matrix notation here. But you can think of things as being finite dimensional, but everything works in infinite dimensions also. Okay, so the problem setup is kind of important. Any questions? All right, so what do we want as our interpolating prediction rule? So if we're in a setting where we can interpolate, right? So the sample size is small compared to the dimension. Then we have a large collection of linear prediction rules that are going to interpolate, and which one of those are we going to choose? The classical statistical theory tells us that there are certainly prediction rules in that set that are going to do really badly. We're going to pick the minimum norm estimator, and one motivation for this is that deep learning methods work with typically simple stochastic gradient approaches that leave you intuitively and also rigorously in an appropriate sense, leave you close to the point at which you started. Right? So you have a random initialization, and then you follow a stochastic gradient approach to find some point in parameter space that minimizes your criterion. It turns out if you do that kind of, well, let's say you do an actual gradient flow in parameter space for this linear setting, you get a minimum norm estimate. Right? So you find, okay, we have, just to introduce notation for our training data, we're going to think of it as, use the classical notation. X is, think of as a matrix with n rows. Each row is one of the xi's. Y is a vector, right, with n elements. Each one is one of those n outcomes. And our estimator is going to be the theta that minimizes the squared error on the training data, and subject to being the minimum, subject to being optimal in this way, is the minimum Euclidean norm parameter vector. Okay, so we're coming up with, among the set of parameters that give optimal squared error on the training data, we're picking the smallest Euclidean norm vector. And the solution to this optimization problem you can write using a pseudo-inverse. Theta hat, our estimate, instead of x transpose x inverse, x transpose y, the classical least square solution, here the inverse in general doesn't exist. And we're going to pick the pseudo-inverse, which is the smallest norm interpolating parameter of the interpolating linear function. Okay, so that's the minimum norm estimator, and we're asking, how well does it perform, and when is this going to predict well? So what do we mean by, so precisely, our performance criterion is the expected squared error of this particular estimate compared to the best we could hope for, right? The optimal prediction error, the expected squared error of the best linear prediction rule. Okay, and we'd like that to get close to 0 as a function of the sample size. So we're concerned with this excess risk, R of theta hat. Okay. Of course, this minimizer is theta star. This thing was, we denoted sigma squared. So we're interested in the expectation of the difference between these two quantities. There's a kind of variance term and a conditional expectation term in each of these. We can split things up and get something that's just in terms of how our theta hat and theta star differs. This is like 2 lines of simple algebra using the fact that the y given x is independent. So y minus the conditional expectation of y given x is independent of that conditional expectation. So the y's have independent noise in them. I guess I should say just uncorrelated, right? Uncorrelated with conditional expectation. So we can write this excess risk in terms of the parameter error, right? Theta star is the best that we could hope for, and theta hat is our estimate. And here we're looking at some notion of the distance between theta hat and theta star, and the right notion is by taking an inner product defined in terms of that covariance matrix of the x's, right? So it's just so our criterion of interest is just a quadratic form involving this theta hat minus theta star. And that's, important, right? So when you think about the role that sigma plays and this spectral decomposition that we wrote, there are these eigenvalues lambda I in different directions. We have to get things right in the big lambda I directions, right? If there's a lot of variance in some direction, then we better get the theta hat close to theta star in that direction, right? Or we're going to be in trouble in terms of predictive accuracy. On the other hand, if some other direction has very low variance, it doesn't matter what we say theta is. Theta hat can be very far from theta star and will predict really accurately. It will not have a big impact on our prediction error. Okay, so these lambda-i's, this is one of the crucial roles that the lambda-i's play. Right? They tell us how important it is to predict theta star accurately in that direction. Okay, so it's quite a classical thing for linear regression. Okay, so let me tell you about the main result here. We can get a characterization of this excess risk in terms of properties of the eigenvalues. So before I state the theorem, let's think about this problem of regularized linear regression. When we work with, so this is classical Tikhonov regularization, right? Where you say, I want to minimize the squared error on the training data plus some other component that depends on the scale of my parameter estimate. And I might add in a component that's weighted by some lambda. All right, so this is a classical kind of regularized risk criterion that we might minimize. We can write that optimization problem in an equivalent way, view this as the Lagrangian of a constrained optimization that says I want to get, subject to a constraint on the scale of my parameter vector, I want to minimize the squared error on the training data. So get the best fit I can for constrained complexity, right, where I define complexity in terms of the norm of the parameter vector. Of course, there's another equivalent constrained optimization problem. So a third form of this where I flip things around, I say I want to minimize this quantity subject to a constraint on that quantity. And this is Lagrangian for both of these optimization problems, right? That optimization problem says, subject to a constraint on the fit to the training data, I want to optimize the scale of the parameter, minimize the complexity. So this is something like what we're doing here in this minimum norm interpolating solution, but we're doing it with a really funny choice of C. So of course, these are three different optimization problems. Given a certain training set, they're equivalent in the sense that there are equivalent choices of these parameters that lead to the same solution, right, in all three cases. But if we view it in this way, we're making a very strange choice of this parameter, right? We're saying set C to 0 and choose the minimum norm solution subject to that constraint. So that's really in the overfitting regime, right? So how small should we expect this to be? The classical approach to analyzing linear regression problems of this sort, particularly regularized approach, I guess motivating regularized empirical risk minimization, is to think about uniform convergence, right? So to say that, for some class of functions, perhaps the class of linear functions that's where the parameter vector satisfies this constraint, I want my expectations and sample averages to be uniformly close, right? And so minimizing a sample average, is a totally fine thing to do because it's close to minimizing an expectation in that case, and that's what I really want to optimize. So, if we're in that regime, then this sample average is going to be uniformly close to an expectation. Well, we certainly shouldn't expect to get this thing much smaller than the best possible expectation, the minimum expected squared error, which is, this sigma squared, this optimal thing over here. If we pick C, this upper bound, much smaller than that, right? In particular, if we're in a noisy problem and we interpolate, this C is 0, this thing is certainly non-zero. So, we're interested in the overfitting regime where we have an optimization problem of this sort where C is in some sense too small, much smaller than you would expect it to be. Okay, so we're asking what happens in that overfitting regime. Okay, so we're setting C to 0. We're wanting to minimize. We're wanting to interpolate. We're necessarily in a setting where the dimension is large enough to do that. This is what our estimator looks like. and we want that min to be 0, so we have to be in kind of n or more directions. When we have this happen, this is a quadratic criterion. Setting it to 0 means that we're actually nailing every prediction, right? y1 is equal to x1 transpose theta hat, right, all the way through to yn. And if we have noisy training data, and that's just the way the world is, you always have noisy training data, then that's a strange thing, right? You're taking the energy of the noise that's in the labels and in some sense injecting it into the theta hat. So all of the noise that's in these y1 through yn labels, training labels, is being pushed into the theta hat estimate. Right? So that's proportional to n. A huge amount of noise energy there that's going in to make our theta hat wrong in some sense. Right? So the question we're really asking is, when can all of that label noise be hidden in theta hat without hurting predictive accuracy? Okay, so here's the result. There are universal constants B and C, so that for any linear regression problem, and I'm just defining it in terms of theta star sigma squared and the covariance matrix sigma, which defines all of these lambda i's, right? It's my phone that's making all this noise, isn't it? Hang on 1 second. All right. So sigma here, the covariance matrix has all of these eigenvalues lambda. We're going to assume we're in this interpolating situation, so lambda n is bigger than 0. We can find n independent directions, and therefore for sample size n, we can get things exactly right. Okay, okay, so we've got a linear regression problem for which we can interpolate. Okay, so now I'm going to use two notions of effective rank, and I'll say what they mean precisely in a moment. The first one is this little rk of sigma. Think of it as the effective rank of the covariance matrix after we step through and ignore the k heaviest directions, the k highest variance directions. So lambda 1 is the highest variance direction. Lambda 2 is in the next highest variance direction. We keep going through lambda k, ignore all of those and look at the remaining subspace. And this rk of sigma is the effective rank of that remaining subspace. So sort of the effective number of directions that have roughly equal variance is the way to think of it. We'll see a precise definition in a moment. Once we get far enough that that effective rank is big compared to the sample size n, remember b here is just a universal constant, let's call that k star. What's that? So, right, so the effective rank here is not the same as the rank, right? So it's rank together with a sort of symmetry condition, eccentricity, low eccentricity condition. So we'll see the definition in a moment, but it's not 0. You have to, it's sort of, yeah, we'll see the definition. It's a ratio of norms of the eigenvalues that are remaining. Anyway, so there's some k where after that point, we reach a k star where this effective rank is big enough, and that k star appears in the upper bound on the excess risk. So this first term, I guess, to give you the highlights of the story to come, the first term is due to the kind of signal part of the y's, right? The conditional expectation of y given x, right, which depends on the theta star. So this is kind of a classical piece that you should expect to be there, that arises because of how our sample covariance is a bit of a distortion of the true covariance, right? That's what's due to this excess risk term, and it nicely decreases as long as the scale of things is not too bad compared to n. The second term is due to the noise, right? So there's signal plus noise. The second term is due to the noise in the labels, right? Grows with the scale of the noise. There's a k star over n term, so we better not have to go too far through the dimensions to find this nice big rank subspace, big effective rank subspace. And then there's an n over r k star here. Capital R is another notion of effective rank. Right? So we'll see in a moment what this is, but we better have a high effective rank compared to the sample size for this term to be small. Okay, so you know, I haven't told you what this is and what it means yet, so bear with me for a moment. But I wanted to point out, so this is a high probability upper bound on excess risk. And you know, if k star is small compared to n and rk star is large compared to n, we could hope for this thing to be quite small as a function of n. And actually, there's a corresponding lower bound, corresponding in the sense that the second term is exactly the same. You know, as long as it's not, this thing is not too big. There's a min of this and 1. Exactly the same as up here, this term due to the noise, but for a constant factor. And the first term, you know, certainly needs to be something increasing with R0 over n. And, you know, you can show that if this is too big, then you do badly. All right, so we could rewrite this lower bound as something that's sort of an increasing function of this thing plus a constant times that thing. So, you know, modulo constants and this sort of lack of precision about the rate that enters into the first term, these are really matching upper and lower bounds. In particular, in terms of the interesting piece, the piece that depends on the noise that's in the labels, we're separated in our upper and lower bounds just by a constant factor. Okay, so this is really a characterization of when we can take that label noise in the noise in the Y's and inject it into our parameter estimates and not suffer from a poor predictive accuracy. So what is this quantity? What do these effective ranks look like? So we have our sequence of eigenvalues. I'm writing them in decreasing order. So lambda 1's the biggest one, lambda 2's next biggest, and so on. So little rk is after we've skipped the first k, the biggest k eigenvalues, so the highest variance directions, we go to k plus 1 and beyond. So we're in some subspace orthogonal to that k-dimensional highest variance subspace. And then for the remaining eigenvalues, the effect of this little rk notion of effective rank is the ratio of the 1 norm to the infinity norm of those remaining vectors. So it's like, you know, how many times can this biggest of those remaining eigenvalues, I should say, how many times can the biggest of this remaining, the remaining eigenvalues fit into, you know, the sum of all of the others? All right, so it's not just the dimension that's left, it's a notion of eccentricity, or symmetry, I guess, the opposite of eccentricity. Okay, so that's the first notion of effective ranks, like a 1 norm of what's left divided by an infinity norm of what's left. The other notion, the capital RK, is a 1 norm squared divided by a 2 norm squared of the remaining lambdas. Okay, so I want to give some examples to give you a bit of intuition about what these different notions of effective rank are like. First of all, there are some simple relationships between them. So the effective rank here is always at least 1. This one is no bigger than this one. And this one's not too much bigger than that one in the sense that you can square the smaller one. And these are easy inequalities to prove. But it tells you that, you know, they're related. They can't be too far apart. But the little one is smaller than the big. Little rk is smaller than big rk. Okay, so there's our definition. Let's think about some easy examples. So if we have a totally symmetric situation, so all of the eigenvalues are equal, then both of these notions of rank are just the dimension. Right? So if the lambdas are the same in every direction, so we have this complete symmetry, then these effective ranks are just the rank. Right? If we're in a finite dimensional situation, then we can write the effective rank as the rank times some notion of symmetry. In both cases, it's a slightly different notion of symmetry. Okay? Now, if things are totally symmetric, you know, we've seen what happens. Scaling things up by a constant, of course, just scales numerator and denominator up by a constant. So if things are constant times the identity, then we just get the rank back, right? This S is just 1. But if things are much more asymmetric, then we can get, you know, and this, of course, is just a rewrite of what we have up there for the k equals 0 case. If things are asymmetric, then, you know, this sort of notion of symmetry might be as small as 1 over p, right? It's 1 over p when the first one is big and everything else is really tiny, right? I said rank p, but right. So you know, essentially 0, very close to 0. We can approach S can approach a value of 1 over p. Okay, so these notions of effective rank are the rank, you know, the number of dimensions that are left times this notion of symmetry, right? It's the rank if we're completely symmetric, and it's much smaller if we're very asymmetric. Okay? So when we go back and look at what's going on here, we're wanting things to be, you know, a very high effective rank. So there are a lot of things that are roughly the same eigenvalues, a lot of directions with in which we have these eigenvalues roughly the same, many more than, so this should be big compared to the sample size. That defines our K star. If we had that situation at the start, right, the K, so to your question, Yasin, if K star were 0 here, then we have, you know, a huge energy in our x's. There's a sort of scaling issue, right? The R0 needs to be small compared to n, and we'd be in trouble in estimating the signal part of the labels, right? So, you know, we need to be in a situation where we've got the first early on the eigenvalues drop, so the sum of all of the eigenvalues shouldn't be too big, and then later we're at a point where when we look at all the subsequent eigenvalues, you know, we have this large effective rank. So they're going to be at some small value, but from then on, they're all close to the same small value, right? We have a lot of symmetry. That's right. The sum of the variance in all of those directions should be small. Otherwise, we're going to be hurting on this first term. But when we get to this K star point, we have a lot of directions where they're small values, but they're all roughly the same. You know, we don't drop fast. We've got a big tail of roughly the same low variance in all of those directions, those more than n directions. Yeah, and that's, you know, necessary and sufficient to get a small error. I guess the other thing is we need this big RK. Once we get up to the right value of k, the K star, this other notion of rank needs to be large compared to n, right? So we have to have large number of directions compared to the sample size that are small but roughly the same. Okay, so that's the characterization and a bit of that intuition about what we need. We need to have many directions where there's not much energy in the x's, not much variance. The dimension of that subspace should be large compared to the sample size. So we have a very high dimensional subspace where the eigenvalues are all small and all roughly the same, roughly sort of equally unimportant in lots and lots of directions. Okay, and so, you know, why does that emerge? Well, there are kind of two competing things going on. We've seen the second one, right? That the eigenvalues tell us how the error in our theta hat affects predictive accuracy, right? If we have an error in the big eigenvalue directions, lambda 1, lambda 2, those guys early on, then that's terrible for predictive accuracy. If we have errors in our theta hat in these later directions, it doesn't matter. We'll still get good accuracy. The other way that the eigenvalues affect things is they determine how the noise in the y's gets distributed across the parameter space. Okay, and it's the interaction of those two that gives the characterization. Okay, and you know, the intuition is that we've got to take all of that noise energy and spread it out somewhere, when we have this long tail of small eigenvalues that are all roughly the same, that gives us a lot of places to hide the noise, where it doesn't matter. It's not going to hurt predictive accuracy. So that's the intuition from the theorem. We need these many parameter directions compared to the sample size in order to get benign overfitting. Okay, so need lots and lots of non-zero eigenvalues. The total, the scale of things should be small compared to n. That was that first term, the signal term. But the number of those small eigenvalues should be large compared to n. And they should be roughly equal. Things can be more asymmetric if we have way more compared to n in some sense, right? This is this notion of rank times symmetry. That sort of intuition about the effect of rank. Okay, so how are we going for time? So we started a little late. How long should I? Okay, great. All right, so let me give you some quick ideas behind the proof. And there's really quite a simple intuition about what's going on, about where the energy is coming, where the energy from the noise in the Ys is going into the parameter estimates, and hence into the predictive accuracy. So as I said, we can think about splitting the excess risk, the excess expected loss, into two components: a component that's due to the signal part, the x transpose theta star, and a component that's due to everything else, the noise part. The first part certainly contributes to the excess expected loss in the sense that it's things are distorted because our finite sample gives us a distorted view of the true covariance of x. Right? The second component, the noise component, is more problematic. So this first one is kind of a classical thing to have to deal with, and even in high dimensions, it's sort of easy to analyze. The second one is more problematic. This is really what's new in this problem, that we're taking this huge noise energy and putting it into our parameter estimate. Okay, so formally the analysis proceeds by defining the noise as, take the optimal linear prediction rule and look at whatever's left, right, in the Ys. We call that epsilon. That's so now this is a vector of length n. Right? Our estimator we can think of, we can write in this way in terms of a pseudo-inverse of x transpose x for our matrix with x has rows that are the covariate vectors, and y is this vector of outcomes. Of course, we can split that y into the signal part and the noise part. And then when we write our excess risk in terms of the difference between our parameter estimate and the theta star, the optimal estimate we could have come up with, we can think about writing that theta hat in terms of this component and this component, right? The signal and the noise component. Okay, when we do that, we get something involving theta star in the signal part and something involving just epsilon in the noise part. And you can work it through. The first part, as I say, is not so interesting. The second part is the new thing that grows with the scale of the signal. It's constant. The approximately equal here is things are concentrated around this value. Right? With high probability, you're very close to this. Okay, so it's something about how far this x transpose x pseudo inverse is from. So how big the trace of the pseudo inverse of that covariance estimate times the covariance. So that's the crucial new term here. And we analyze it by looking in the different directions, the directions defined by the spectral decomposition of sigma. Right? So there's the highest variance direction, the lambda 1 direction. This corresponds to this V1, and then there's a V2 and so on. We step down through those directions, split things up into the heavier directions, the bigger values of lambda I, and the lighter directions, right, the smaller ones. So there's some point where we switch from thinking of it as a heavy direction to thinking of it as a light direction. And turns out that when you think about the concentration of the non-zero eigenvalues of the sample covariance. So, we come up with, this thing is a scaled sample covariance, right? It's sort of like scaled average of these XX transposes, outer products, right? So that has an expectation that's exactly sigma, but when we take the sum of n of these things, we get n times a sample average of that thing. And that's only got n non-zero eigenvalues, right? Because we're in a very high dimension. And we want to know, what goes on with those eigenvalues. So it turns out that when we have this condition satisfied, that the effective rank beyond k is big compared to n, then when we look at those k plus 1 through n non-zero eigenvalues, they're all concentrated around a particular value. So this condition is enough to ensure that they're concentrated around a specific value that we can identify that depends on the eigenvalue, pattern of eigenvalues. So, this is just a sufficient condition to get a handle on those. And, for some intuition, you can think about if we take, instead of X transpose X, we take the Gram matrix, which is this n by n matrix, then it's got all n of its eigenvalues bounded away from 0, right? Which is the same thing as, the eigenvalues, the non-zero eigenvalues of this n by n matrix and this P by P matrix, where P is really big, but it's only rank n, only rank n matrix. Those non-zero eigenvalues, of course, are the same. And all of these, the non-zero eigenvalues in the two cases are bigger than, at least as big as this row. Okay, so, that should bring to mind what goes on in ridge regression, right? When we introduce regularization in a ridge regression setting, so that first regularized risk criterion that I put up there, regularized empirical risk criterion, the solution to it is X transpose X plus, I called it lambda, but let's think of it as lambda. X transpose X plus lambda I to the minus 1 times X transpose Y. That's the solution. You should think of that as something like what's going on here, right? Because when we take our pseudo-inverse, we're saying actually all of the eigenvalues are at least rho, right? So rather than adding in something that keeps things above a certain level in this matrix, right, we can work with a matrix and guarantee that things are above a certain level. Okay. All right, so a little intuition doesn't actually play a part in the proof. Okay, so I think the key idea here is you can think about where, there's the signal part that I've omitted here and the noise part, and we're taking that noise, which has an energy proportional to n, right? We've got n kind of independent pieces of noise, and we're injecting that noise into the theta hat. You can try to keep track of where the energy from that noise goes. So let's split things into, we multiply it by this X transpose. So we're looking in different directions. Let's think about what happens in different directions. X has a covariance that's got, in the lambda 1 direction, V1, there's a lot of covariance that way. So a lot of the noise is going to go in that direction, right? So for that V1 component, we're going to put the energy, we're going to get some energy in that direction here that's proportional to n times lambda 1, right? And so on in all the other directions. And I'm speaking vaguely because X is sampled, right? So in expectation, that's where the energy is going to go. It gets scaled by this pseudo-inverse. Now that either chops things down to 0 or, scales them according to 1 over the corresponding eigenvalues. Okay, but we know all the non-zero eigenvalues are at least as big as this row. Okay, so things get scaled up by no more than 1 over rho, and we're considering energy, so we should square that. Right? It's no more than 1 over rho squared that our energy gets multiplied by. And then, of course, the impact on the prediction error is scaled by another factor of lambda I, because we're talking now about the effect of the noise, just this additive error in our parameter estimate. Well, that additive error is going to come into our prediction error scaled by, the corresponding eigenvalue of the covariance matrix. So there's another factor of lambda I. So put those things together, you get an n times lambda I times 1 over rho squared. Okay, waving my hands because again, this is just in expectation. Turns out this is the right calculation in the in the light directions. In the heavy directions, we can do something better. We get something that, things are never worse than kind of 1 over n. And there's, a Sherman-Morrison kind of trick to get this. And add up all of these directions. There are k directions like this. They give us a k over n. All of the others, we're summing up across these other directions, something like the lambda I squared over rho squared, which is exactly this kind of quantity that we saw. Okay, so you can think of it as just keeping a tally of where that energy goes and what impact does it then have on the prediction error. Okay, the lower bound, very similar story actually. It looks somewhat, going back here, this looks somewhat arbitrary. We're saying if we have this condition satisfied, then we've got nice concentration and everything's good, but turns out it's necessary as well. You can do a calculation on the other side, and if you don't have these eigenvalues concentrated, then you're bigger than some constant. So you're in trouble. Right? So this is where these necessary and sufficient conditions come from. Okay, so that's the main theorem. And it gives us something quite precise for any sample size, any particular covariance matrix. But one natural thing to ask is, well, so what situations are going to have small excess risk? When are we going to be in this benign overfitting situation? What does it really mean in terms of patterns of eigenvalues? And we might think about, just asymptotics. Just we want, as n gets large, that first term should go to 0, the second term should go to 0, and the third term should go to 0. Okay, when does that happen? And think now about, a particular infinite dimensional covariance matrix. Okay, so it turns out in the infinite dimensional case, this is a really hard condition to satisfy. You've got to be right at the edge of being summable. You have to be summable for the first term to go to 0. But in order to have these other two terms to go to 0, you have to be only just summable. So if you want lambda I to be something like a polynomial, 1 over a polynomial times 1 over, we have to put the log factor in, then we want this alpha, it's an if and only if. We want that alpha to be 1 and the beta to be greater than 1. Okay, so we're just at the edge of summability. And it's an if and only if, right? So you can't have the eigenvalues decreasing quickly or you're in trouble. So that makes it look like, this benign overfitting phenomenon is a really unusual thing, right? And certainly in the infinite dimensional setting, that's true. On the other hand, there's a much more generic setting where you can show that benign overfitting occurs, and that is when we think about our eigenvalues as something rapidly decreasing plus some constant level, right? So we have our eigenvalues decreasing really fast, and then across some finite dimensional subspace, we have isotropic noise, right? That's what this epsilon looks like. And as n increases, we might think about a bigger and bigger subspace, a bigger and bigger dimension, okay? So if you look at a sequence of problems like this, then all we need is that this dimension is large compared to n, that the total energy, that's the isotropic energy, is small compared to n, but it can't be 0, can't be ridiculously small, and then we're good. Okay, so this is a pretty, so if we're in the sort of essentially infinite dimensional, but we clip things, like neural nets, which are very large but clipped at some finite dimension, then we're in good shape. And you can quantify things quite nicely here. Okay, so this seems much more like a universal phenomenon. The fast converging part could be anything. This epsilon n, it could be something really super tiny. That's a weak condition there. Okay, so let me finish up. You can go beyond the Gaussian case to sub-Gaussian noise, sub-Gaussian X's. There are lots of open questions. Even in the linear case, we don't know how to work with things that are misspecified, so we don't have the linear model being correct. We don't know how to get by with less independence than this condition requires, which, for instance, for kernels, we don't know how to deal with that. There have been some advances in these directions, as long as you're allowing the input dimension to get large. You need sort of the independence to grow in some sense. How's it related to deep learning? Excuse me. So there are these linear views of deep learning methods, these neural tangent kernel kind of views. They're not really, the results that we give don't extend to those cases, to that sort of an infinite dimensional setting. So there's a lot of work, I think, to understand what goes on in those cases to get the same sort of characterizations we have in those cases. And the neural tangent kernel kind of assumptions are a little unusual. Okay. So there's this other phenomenon of adversarial examples in deep learning. In the linear regression setting, it's really clear that you should expect that to happen, and it's an if and only if, right? If you're in the setting of benign overfitting, then there is a direction where the noise is appearing, right? You're taking all the noise in the Y's and you're putting it into your parameters, so you've got some direction where things are incredibly sensitive, and sensitive in a way that's sort of 1 over one of the terms in the upper bound on excess risk. So if you're doing well in terms of benign overfitting, then you've got to have some direction where you're really sensitive to perturbations of the input. Okay, so it goes along with being in this overfitting regime. It's sort of an inevitable consequence of benign overfitting. Possibly the same thing is true in a deep learning setting. Okay, lots of future directions. I think the most interesting of these is what can we say about the deep network setting? Nonlinear functions. As I say, it's just a first step to understand what goes on in a linear setting, but it's not useful methodology in a linear setting. It's just really what we'd like to do is understand what goes on with this benign overfitting phenomenon in deep networks. Okay, so key point is that for benign overfitting in linear regression, we have to have lots and lots of unimportant parameter directions where the noise can be hidden. Stop there.